Houston, we have a podcast. Welcome to the official podcast of the NASA Johnson Space Center, episode 30, Infamous Meteorites. I'm Gary Jordan, and I'll be your host today. So on this podcast, we bring in the experts, NASA scientists, engineers, astronauts, all to let you know the coolest stuff about what's going on right here at NASA. So today, we're talking about some of the more unique findings that have been discovered in meteorites with David Mittelfeld, goes by Duck. He's a planetary scientist here at the NASA Johnson Space Center in Houston, Texas. And we had a great discussion about curious findings in meteorites and the adventures that are endured to procure them. So, with no further delay, let's go light speed and jump right ahead to our talk with Dr. Duck Mittelfeld. Enjoy.
T-minus 5 seconds and counting. Mark. All launch commit lights are correct. There she goes.
Houston, we have a podcast.
Duck, thanks for coming to the podcast today. I know we've talked about searching for life in meteorites before, and it's such a fascinating topic. But I really wanted to dive deeper just into like the meteorites portion. We really actually had a great conversation with Dr. Aaron Burton and Dr. Mark Fries not too long ago, actually, about life, but really just about the meteorites themselves. There's a big story there, and you're one of the explorers that are going down and actually finding these meteorites, huh?
Yeah, I've done that on a number of occasions.
Yeah, and it's is it mostly in Antarctica, or are you going other places?
Well, okay, so most of the times I've been searching for meteorites has been in Antarctica, so I've been down there 5 times on meteorite collecting expeditions.
Wow.
But I was on vacation in Israel once, and I met up with a couple of geologists at a coffee house, and one of them had just published a paper where he described old surfaces in the deserts of southern Israel that are have been stable for about 2 million years. And I'm thinking, over 2 million years, you can accumulate a lot of meteorites. So I actually went there later that year and met up with them again, and we searched some of these areas that have very ancient pavements on the desert. And hunting for meteorites, we didn't find any, unfortunately. And I'm not quite sure why. There should have been some there, but it was a small team searching large area over a short time. So it may well be that they're there, but we just didn't find any because the ones that are there are small. The other is there were a number of issues with that particular location. Meteorites, when we find meteorites, they're typically black on the outside because they've gone through the atmosphere and they're covered with this glassy fusion crust, which is almost always black. The area we had searched in southern Israel actually had a number of dark rocks in it as well. So, the meteorites, if they were there, would not have stood out as like the beacons that you see when you're in Antarctica scooting across bare ice. So
I guess that the main reason why Antarctica is such a great place to find meteorites is because it's these black rocks against white snow.
Well, that certainly makes it easy because you can see a rock. I'm going to use metric units because that's what I'm used to. I'll try and remember to throw in inches and feet as I can. But,
sure.
So you can find a black rock a couple centimeters across or about an inch across from a great distance in Antarctica on the ice. And as you say, it's because you're looking at either pale blue ice or sometimes white snow. Mm-hmm. Most of the meteorites we find are on the pale blue ice, but even so, it's very bright in comparison to rock. So they're easy to find there. The other thing is in Antarctica, we have a convenient concentration mechanism, which is the actual flow and ablation of the ice across the continent. And where we go to find the meteorites is actually in locations where the ice movement has been stalled, and ablation by the Antarctic winds and warming by the Antarctic sun allow a lag deposit to develop on the surface. So we're actually collecting meteorites that have been, shoved from a great geographic area and then left behind in a smaller geographic area. So we have, we have both the easy to spot and the concentration mechanism working in our favor.
All right. Yeah, they're plentiful down there. So you made quite a few trips. How many was it? You said 5?
Yeah, I've been down 5 times. The first time was in the 97, 98 field season. That was my first Antarctic experience, and I loved it so much I kept volunteering to go back again.
You loved Antarctica.
Oh yeah, I love it. You know.
Yeah.
You just last week, well, here in Houston, we had temperatures that Houstonians think of or Texans think of as cold, but
Right.
I see that as maybe a cold fall day, because I was born and raised in Western New York.
All right.
And at the same time, you know, my hometown was getting temperatures. Okay, again, I've got to do some conversion here. About maybe between 0 and 5 degrees Fahrenheit.
Ooh.
And you know, that was the weather I grew up with in winter, and I loved it. That winter was always my favorite season when I was a kid.
All right.
So
maybe it's a deep level winter that really, because I just came from this. We're just coming back from the holidays now, and it was -2 in Pittsburgh when I was flying home. And I mean, I was born and raised in Pennsylvania, moved around a lot, but I'm not used to it by any means. Like I like the everyone, you know, saying, "Oh my gosh, 32 is really cold." I'm okay with just that.
No. For me, I love the deep winter in Western New York.
All right. A lot of snow there too. So when was the last time you were down in Antarctica then?
So I was down last year, 2016, 2017. It was kind of a disappointment for me personally.
Oh.
I because of my experience, I've been down 4 times before. I left early and was going to go out on a recon sweep with the Mountaineer Field Safety Officer for the ANSMET program. ANSMET, by the way, stands for Antarctic Search for Meteorites, and that's the program that goes down to collect the rocks and has been doing so every year but one since 1976.
All right.
But anyway, because of my experience, I was going to go down on this recon before the main season. We were going to go to one area, check it out for potential systematic work in a future season, and then stay for the first half of the main season going to a location deep along the transantarctic mountains. Well, it turns out logistics were badly broken last year.
Ooh.
And partly because of weather, partly because of problems with the aircraft and so on. So I got out into the field for a week in preseason. I got back to McMurdo Station while we were gearing up for the main season, but the logistics just broke, and so they were not going to go out where they originally planned. The team ended up going to where I had been out on recon, but they got such a late start that it made more sense to ship me home early rather than go out for maybe a week and then come back into McMurdo and go home.
Yeah.
So I just spent 1 week out in the field last year, much to my chagrin.
So it was just the lack of time that you spent there that was really the disappointment.
Yeah, it was lack of time. And in the brief time that John Scott and he's the mountaineer, were out on the ice. We spent a week in the field, 2.5 days. We were tent bound because the weather was so bad. But even so, we found 46 meteorites in the short time we were there.
That's amazing.
Yeah.
Wow.
And remember, this was an area that had been heavily harvested back in the 80s, 70s and 80s. We were going back to see whether there was still great potential for harvesting more meteorites there. And in fact, I think last year they ended up coming back, picking up a total of 200 and some meteorites, even with going back to an area that had been searched before and having shortened season because of logistics. So, I mean, that kind of shows you the quality of Antarctica as a site for bringing back space rocks. It's just awesome.
Incredible. So is that is it because there's just a fresh, I guess you can call it, supply of meteorites that are landing on the surface of Antarctica, or is it things are shifting?
It's more things are shifting.
Okay.
In part, deflation of the surface continues as ablation goes on, and so new meteorites are poking through.
I see.
In part, it's shifting winds blowing snow around, so an area that might have been snow-covered earlier season maybe now has been stripped bare and there's bare ice. And so
Okay.
that allows you to see things. So for a variety of reasons, you can go back to the same place you've searched once and still find meteorites out there.
Incredible, and hundreds of them. A little bit better
Yeah.
than Israel, right? With
Yeah,
with
yeah.
an
Quite a
astounding
bit
0.
better than my experience trying to find meteorites in the Negev desert.
So you're saying a season. When you're going down to Antarctica, I'm assuming it's the summer there, right? It's when
Yep, it's austral summer.
yeah. So that means the sun is up 24/7, right?
Right.
So you kind of have to deal with that when you're down there, right?
Yeah, I've become accustomed to that. The first I was kind of there was a guy who used to work in our building who had been down I think a year or two before me. So I took advice from him, and he said, one of the things is with the constant sunlight, sometimes sleep can be a problem. So I bought a heavy black knit hat, and I just put that on as my sleep hat, and then pulled the brim over my eyes, and so everything was black. So I could sleep fine down there.
Oh, nice.
But the main advantage is that because the sun's up 24/7, you're not really bound by the 9 to 5 time sequence. So
Oh, yeah.
as I said, when I was out last year in the recon site, we were there for a week. We landed, got our gear, and then spent half a day out. And then the winds blew in. It was too windy and cold to go out. So the winds broke around noon one day, or a little bit after noon. We decided we would have an early supper and then go out and harvest meteorites. So that day we ended up getting out of the tents maybe 5 o'clock in the evening, and we worked till about 1:32 in the morning.
Whoa.
The sun was up; it was perfectly fine. It was just my aged body crapping out at 1:30. I just couldn't pick up another meteorite if they beat me with a stick. I was just so
Wow.
tired. But that's something you can do down there that you can't do here.
Yeah. Did you know the hours were going by, or did you have no sense of time with the sun being up?
Well, you can trace the sun. If you pay attention, you can get a sense of the day because the sun does a lazy loop in the sky.
Oh.
And so, once you've located yourself, you know where north-south is. There is still north and south, even that close to the pole.
Yeah.
But at midnight the sun is going to be at one position. So
Right.
and it's kind of at the lowest point far north, and so you can track it that way. But basically, I didn't pay attention. We were just so busy, driving from place to place harvesting meteorites that. It was just constantly moving, doing the next one, taking the data, collecting it, cleanly and safely, and getting it in the bag and moving on to the next location.
Oh, so are you not you're not stationary then when you kind of set up camp? Are you kind of mobile like with your camp and you just move it from one meteorite site?
No. The camp
okay.
the camp is usually there are a couple of ways that is done. When we do systematic searching, the camp is stationary in one spot, perhaps for the whole field season.
Okay.
And you just go out day to day to different locations.
Oh.
And that's what we did here. We were on recon, so we plunked the tent down, and then we searched within easy skidoo range of the camp. Sometimes, and I've done this before, go down on a recon team where we go and you put camp down. You might prospect an area for 2-3 weeks, then you move camp to another area and prospect there for 2 or 3 weeks. So there are both those. There are those two types of scenarios, and even in the recon mode, the tent is the camp is stationary for 2 or 3 weeks, and you're skidooing all around that area to search it, and then you only pick up tents and camp and move to a far distant area to recon that general region.
All right.
So.
All right. Well, I'm guessing, going down there so many times, you're quite an expert in making sure that, you can survive weeks and weeks and weeks in Antarctica. So what are some of the stuff that you're taking down there that I guess are unique to the Antarctic environment?
Okay, so most of the gear you get in Christchurch. So, living in Houston, I don't have a winter coat.
Oh.
So at the clothing distribution center in Christchurch, you'll get outfitted with heavy jackets, all the gloves you can want, thermal pants, fleece liners, boots, hats.
All right.
Everything you need to survive. And then in McMurdo Station, you actually get the camping gear, the tents, the cook stoves, the dishes, the food, sleeping bags, that sort of stuff. So all the intrepid Antarctic explorer needs to take down with them are personal items. Like I mentioned, my knit hat, that was mine, and
Oh, okay.
that was because I knew wanted something to sleep in. I bought extra pairs of thermal underwear because the first time I went down, they give you 2 sets, but you're out in the field for 6 or 7 weeks, so
Ooh, yeah.
you want to change, once in a while.
Probably.
Other than that, my glasses are prescription, and so I buy glasses that transition dark in sunlight, so I can just wear my normal glasses out on the skidoo. I have actually bought glacier glasses, so I have side shields and whatnot to block the light. One of the things that really is critical down there is to block out all light from your eyeballs, other than what gets filtered through a dark lens. Because otherwise snow blindness is a problem.
Oh, that's right. It's so bright down there, right? Yeah.
So I do that, but otherwise, most of the gear they give you, they loan it to you for the time that you're out there, and so you could survive on just what you get from the Antarctic program down in Antarctica. You wouldn't necessarily be entirely comfortable wearing the same clothes, for 7 weeks, but you could do it.
So your this Antarctic program that's ANSMET, right?
Right.
Okay. So what's the relationship between ANSMET and NASA and how that all works together?
Well, originally ANSMET was set up as a 3-agency agreement. So it was funded. The actual Antarctic search for meteorites was funded through the National Science Foundation because they have they do the scientific research in Antarctica.
Okay.
NASA funded the curation and allocation of meteorite samples here at NASA Johnson Space Center. And then the Smithsonian Institution did the initial classification and was the long-term repository for the meteorites collected in Antarctica. Since then they've changed it, and now NASA actually funds the Antarctic, the ANSMET research component. NSF still supplies the logistics, but NASA pays NSF for those logistics because they are they have all the logistics in Antarctica.
Yeah.
And the rocks still go ultimately to the Smithsonian, a chip for initial classification, and rocks that are no longer actively being researched by scientists in the world end up being permanently curated at the Smithsonian Institution. So that is still the way things are run.
All right. So is the ones that people are researching and actively studying, are all of them housed here at the Johnson Space Center?
Yes, with some exceptions. We don't have the necessary facilities to easily deal with metal-rich meteorites. So iron meteorites, stony iron meteorites automatically go... nope, I'm going to pull that back. Iron meteorites automatically go to the Smithsonian Institution.
Oh.
Because they are equipped to cut metal and make samples available. We do the stony meteorites here. I forgot about that because I've gotten some from here. So those that have a significant stony component are still worked on here until they become no longer of scientific interest.
Okay.
But even though they go to the Smithsonian for permanent curation, they're not dead to science, so to speak. So I can request samples that have been housed at Johnson Space Center for years and now transformed permanently to the Smithsonian if I find an interesting project to do on one of these old samples. And I actually have gotten in the past some samples from the Smithsonian that were originally from the Antarctic collection.
Wow. So back in Antarctica, when you're looking at these meteorites and you're trying to, figure out what they are they, more stony, more metal rich? What are you using to look at them, to find out more about them and say, yes, that's a meteorite that I want to get my hands on? How do you know what's the good stuff?
Decades of experience.
There you go.
So I can look at a rock in Antarctica, and I can already make a preliminary classification.
Really? Wow.
Sometimes I'm wrong, and the guy who has more experience than anyone is our Mountaineer Field Safety Officer, John Scott, and he can look at a rock and in many cases give a pretty good guess as to what it's going to turn out to be. And I can do that with a lot of different types of rocks, especially those that I'm interested in. But all in all, there are always those meteorites that come back that either no one has ever seen before because it's totally new, or it's enough different from the norm for that class that it just doesn't appear to be what you think it is in hand sample. So we don't, in Antarctica, we don't do any more than a very high level classification. Yes, this is a stony meteorite. It's probably a chondrite. This is probably a carbonaceous chondrite. This is probably an achondrite, which is a type of meteorite that's been melted. This is probably a stony iron, an iron, and so forth. To some extent, we need to do that because certain types of meteorites have more scientific value than others. So for example, a very primitive carbonaceous chondrite is probably going to get a lot of research attention when it's announced. And so we collect those in a special way to try and minimize contamination by organic compounds. And that's why we need to be able to say, oh yeah, stand back from this guy. We need to treat him differently than this one over here.
All right. And then, obviously, knowing where to ship it, too, right? Because some of the metal ones have to go to the Smithsonian, some of the carbonaceous ones.
No, that's all done here. Everything is shipped here to Johnson Space Center.
Oh, everything comes here.
Right.
Okay.
But the difference is when they open some that are listed in the notes as probably being iron meteorites, they will warm them up in the dry nitrogen cabinets, look at them, and if they agree, they'll do an external description. This is a brown rock, 10 centimeters in size and weighs so much, and we don't see anything in it, out of the ordinary from the outside. Then that whole rock will get shipped to the Smithsonian at that point. And there they'll cut it open with a wire saw, if it's, indeed probably metal, and then make a polished mount and etch it to bring out the texture and so forth.
All right. And that's what you mean by the facilities, right? They have the proper facilities to do that. So what about here? What kinds of equipment and facilities do we have to make sure that we're handling all of this properly?
In the meteorite processing lab, we use tools of a very limited set of composition. So typically stainless steel hammers and chisels. And the reason is, no matter what we do with a rock from space, we're going to contaminate it with something from Earth. So the object is to, one, minimize that contamination. So we use materials that we know are not going to, just shed particles everywhere, for example.
Right.
But also, if we use always the tools of a given composition, so that we know that if we see something like this in the rock, oh yeah, that must have come from the tool. And I've seen this. The rocks are hard to break, and so your choices are to saw them open or to use a hammer and chisel. And I have seen on a rock that I've gotten a flake from the chisel that rubbed off. Metal, it's soft. Even hardened steel will rub off on occasion. So, I could see this. I can pull that contaminant off or isolate it in the lab. But, I know then I can do a simple test. Yes, that's from the chisel. I don't have to worry about that. I've taken care of it. The rest of the sample is fine. So the object is to minimize contamination or to know what the potential contaminants are. And, there's no way to with modern technology, we can't we don't have magnetic levitation devices that we can then use a laser to slice them open cleanly. We do with what we got.
That's
this
right.
isn't Star Trek here yet.
We'll stick with the hammer and chisel for now. So, I mean, when you're cutting these open and you open them up, what are you looking at? Are you looking at just the rock, or are you taking even smaller chunks of that? How is that working?
Well, that all depends on the question that you're trying to answer. And I've done both, where I've asked for samples of what's called a bulk sample of the rock, so something as representative of the entire rock as possible. And I've looked for individual clasts in the rock, little fragments that are of a specific type within the rock. All of this is basic 19th century geology in many respects. In the 19th century, geologists would go out in the field with their hammers. They'd beat on a rock and use a hand lens to look at the microscopic texture, mineralogy in it. And a trained geologist can do the same with a meteorite and say, yeah, okay, I can see what this is. It's a certain type of rock type in there, and that's what I want. I don't want this part over here. Traditional geologic methods, but with modern equipment, can be used. And there's nothing like the human eye and the brain for sorting out who's who in the zoo.
So then how can you, what are some of the key differences for the non-geologically trained eye for when you're looking at a rock and you can, you cut it open and you look and you say, that's a meteorite, that's not from Earth, or this is definitely from an Earth.
Yeah. Okay. Earth. So the first key is fusion crust. I mentioned this earlier.
Yeah.
And that's where going through the atmosphere, friction with the air causes the outer surface to melt, and actually, little bits are flying off all the time. Mm-hmm. The meteorite we get on the surface is just a small piece of what entered the atmosphere. Sometimes the vast majority of it just ablated away in the atmosphere into little droplets or dust.
Wow.
If you see a fusion crust on the rock, right away it's a meteorite. You don't have to go any farther than that. In terms of determining what type it is, more primitive meteorites, these are a type that still have textures and mineralogy that were inherited from condensation and accretion in the solar nebula. That's where individual mineral grains formed out of the gas that was the nebula before the planets were around. Wow. And then they agglomerate together, these mineral grains, and in the solar nebula, the dust grains got melted into little tiny objects which we call chondrules. So these typical textures are plainly evident to the human eye, even without a microscope. But with a very low power microscope, you can see them quite easily. Most meteorites, especially primitive ones, contain iron metal. It's actually iron nickel metal. You don't find that on Earth except when humans have been involved in smelting iron ore. So iron metal in a rock is kind of an indicator that it's quite likely from outer space. Very few occurrences on Earth of native metal in a rock. And then, as I said, in the dust in the solar nebula went through periods of melting and formation of these little round globules of basically melt globules, which we call chondrules. And from that, we got the name chondrite for these primitive rocks. Mm-hmm. Well, those stand out if you break open a rock, depending on the type, you can see those quite easily, and that's a key.
And these they've been in space for all of time, right? They've formed in space and traveling through space. They're not like from another planet or another, like chipped off another asteroid or something.
Actually, all meteorites, the only way we get meteorites is for bad things to happen in the asteroid belt. Most meteorites are from asteroids, and when they collide, little fragments get knocked off, and it's from these fragments that we get meteorites. So they were originally on much larger bodies. I mean, much larger meaning asteroid size, not planet size.
Okay.
And they were broken up and then distributed to the Earth. One of the sorry, I'm going to sort of go back get into my Wayback Machine and go back to when I was a grad student.
Please do.
When I first started learning about meteorites, one of the mysteries at the time was there was a group of chondrite meteorites called the L chondrites. L was just the name, the name applied to them, that had ages of on the order of 500 million years. And this was really odd because all meteorites are about 4.5 billion years old. Well, these meteorites were originally about 4.5 billion years old, but were somehow affected by an event that reset the ages about 500 million years ago.
Whoa.
And so, this was, just kind of an anomaly. We knew something bad had happened to an asteroid then about that time. Well, fast forward to, I think, the 90s, a Swedish geologist started finding in terrestrial sediments fossil meteorites. And, all that's left is a few mineral grains. You can tell they were found in fine-grained limestone, formed on an ocean floor. Mm-hmm. And all that you could see was this halo of odd stuff plus a few mineral grains that remained from the original meteorite. Well, this guy and his compadres studied these mineral grains, and they found out they were from the same type of meteorite as these chondrites that were about 500 million years old. Huh. And they were in layers in the rock of the Earth that were about that age. So sometime 500 million years ago, a couple asteroids collided, and a whole rain of meteorites of this type hit the Earth at about, within a few million years of when that occurred. And we can find them now, this layer in Sweden that's just chock full of these fossil meteorites. And, to me, that's one of these really neat kind of science stories where everything starts tying together. Yeah. And then to get even further, astronomers looking at what they call asteroid families. So they find an asteroid, they find a whole bunch in orbits similar to it. Spectroscopically, they all look to be about the same. And so they figure out, well, these are all fragments of something that broke apart. Well, they found an asteroid that they figure, based on the spectroscopy, it could be this type of asteroid that formed these L chondrites. And what they calculate the age of the family based on dispersion of the fragments, and it's about 500 million years. So, between, meteorite scientists, terrestrial geologists, and astronomers, we've kind of got a neat picture of somehow, about the time of dawn of multicellular life on Earth, and two asteroids smashed together and rained out on the Earth, and we're still finding fragments coming down to Earth now that we can confidently date when this happened in terrestrial laboratories. It's just kind of one of these things that I find fascinating.
I find it I mean, a lot of this is over my head because I don't have the same background as you, but I just find it fascinating that you can look at these rocks and get a story out of it. Like the story of two asteroids around the time that cellular life was developing, coming down to Earth and raining down in these locations and telling this story. That's fantastic.
Yeah, and multicellular. So this is when fossils, shortly after the time when fossils started becoming really abundant in the terrestrial record.
Wow.
So, it's just a neat story. And, basically, I think that's what got me into geology originally was, all you've got is a rock on the surface of the Earth. And somehow you can, if you're smart enough and do the right work, you can start to piece together an entire story of what the Earth was like at that time. And so, that's kind of what drew me into geology.
That's fantastic. I love it, especially from my background, the marketing and journalistic sort of background. The storytelling aspect is just fascinating to me. And that's kind of like that, the title of this episode is going to be Infamous Meteorites. And that's kind of like what I really wanted to dive into is, we've talked about where you're finding these meteorites and then what you're doing with them. You're actually cracking them open and studying them. But then what are you finding? What are you finding inside of these meteorites? What stories?
Yeah, well, exactly.
Yeah. So one of the ones that I know that was brought to my attention was one of them called Allen Hills, and is it 84001, or do you call it by something else?
No, I call it that.
84001? Okay.
Or sometimes it's simply referred to as that rock.
Because it's that infamous, huh?
Yeah.
Wow. All right, so what's the story behind this rock?
Okay, so this was found in Antarctica in 1984, and it was originally classified as a type of asteroidal igneous rock that at the time I was studying those types of rocks. My background is heavily weighted towards an interest in magmatic processes on the Earth, the Moon, Mars, and asteroids, and so that's why this one was particularly of interest to me. So I was studying that along with a bunch of others that were thought to be basically the same classification of rock, and unfortunately, Allen Hills had some puzzling features in it that were a little bit off normal for that rock type, but not so much so that I really stayed up at night worrying about it. So I wrote a paper on this group of rocks finally, and sent it in. And one of the reviewers said, well, you point out that there is this anomaly in this rock, and you really ought to try and chase down what's going on there, why it's different. Mm-hmm. And, being a moderately good scientist, I said, okay, he has pointed out it's a problem. I knew it was a problem, but now I've really got to do something about it. So I started working at it, and honestly, I could not find out what was wrong with this particular rock. Mm-hmm. There was one mineral phase in it just did not match what one would expect for the class. Quite by chance, I got another sample of that rock for another reason, but it really wasn't the sample I had asked for. So there was a mix-up in the thin section. So a thin section is a very thin slice of a rock. It's about 30 microns thick, doubly polished on both sides, and it's used by people who look through microscopes to look at the minerals and textures in a rock, and then you can put that section into an electron microprobe and actually do analyses of the mineral phases in it. Wow. And so that's what I was interested in. In this particular rock, which I thought I had, I was interested in the composition of sulfide phases in the rock. So I put the sample in the electron microprobe without actually looking at it in the microscope first, because I had seen this rock before. I knew what it was like. I knew what to expect. I just went straight to the electron microprobe, which actually probably was good, because I may have turned the rock in and asked for a different one otherwise. But I'm getting it. I'm looking at it in the microprobe, looking for the mineral phases I'm looking for, and they just really aren't there in the abundance that I expected. Finally, I found a grain, and I'm banging away at it with the electron beam, collecting compositions, and the compositions weren't making sense. I was expecting it to be, so I was looking for sulfide phases, so I was expecting to have an iron monosulfide, so one iron, one sulfur atom, and the composition that was coming out just was not right. And I checked the calibration. The calibration was perfect. So what's going on? I was looking at the data not in atoms, but in mass, so weight percent. So when I converted it to atoms, I realized I had 2 sulfur atoms for every iron atom instead of 1. And that's when it hit me what was wrong with this rock. I then backed off, looked at the texture in more detail in the electron microprobe, and realized I had a sample of Allen Hills, not the meteorite I thought I had. Oh. And I knew which type of rocks had pyrite, the iron disulfide, instead of the iron monosulfide, and I knew those were Martian rocks. And so, it was probably the most satisfying moment I've ever had in my life,
Wow.
excluding when my children were born and when I got married. And if my wife listens to this, I hope she hears that.
Priorities.
Suddenly it dawned on me that this was a Martian rock that was totally unlike any other Martian rock, except the key minerals were in it. And so, it was just one of these aha moments that you live for. It was just so much fun.
Amazing.
I tell you.
So what were the key minerals? What story did they tell?
So the key was because it had the iron disulfide pyrite instead of the iron monosulfide troilite, I knew it was Martian. And it was a rock type not known amongst the Martian meteorites. So what it meant was we had a new type of Martian rock that was going to tell us even more about the geologic evolution of Mars than we already knew. All of this hit me within like a fraction of a second when I realized what it was.
Wow.
So, I immediately recognized that it was an important meteorite. And that it would tell us big things. And in fact, it has opened up a whole host of, basically this rock ultimately became a founding member of what you might consider astrobiology. And that came when my colleagues here at Johnson Space Center, Dave McKay, Everett Gibson, and Kathy Thomas, and now Simon Clement is added, and then there were Simon's dissertation advisor at Stanford was on the paper, and several other people.
Mm-hmm.
They proposed that a certain both mineralogical and compositional and textural objects in this rock were possibly signs of microscopic life that existed on Mars at one point.
Wow.
And, to some extent, then this really allowed the whole discipline of astrobiology to blossom, because suddenly we had to figure out, how do we understand how can we possibly search for life in other objects, other planets? What do we need to look for? Because we're used to looking for life on Earth. It's simple. Just walking over here, I had to wait while an opossum walked past me in front of on the walkway. Life is everywhere on Earth.
Yeah.
Whereas on Mars, maybe it's not everywhere. And if it was there, how are we going to tell that it was there?
Mm-hmm.
What do we need to do? So I would say the import of Allen Hills is not so much that it was hypothesized that fossils of life are in that rock, but that it caused scientists to really take a much more rigorous look at how they will search for life other places of the universe.
Wow. And that's kind of, like you said, the birth, well, maybe not the birth, but really the blossoming. That was the word you used of astrobiology, life forming outside of Earth. It's just a wild concept.
Yeah.
How is that even possible?
Yeah. And, the other thing is it was a strong impetus to driving NASA's Mars exploration program. It is a lot of it is geared towards finding evidence for habitability locations on Mars, and ultimately, if from locations where we think there may have been a chance for life, bringing back or studying in situ samples for possible evidence of microbial or larger life on Mars.
Yeah. And you said you were, before we started recording, you said you actually were working with Opportunity, too, one of the rovers on Mars.
Yeah. In 2005, I got attached to the Mars Exploration Rover mission.
Yeah.
At the time, we had two rovers going, one Spirit in Gusev Crater and the other Opportunity in Meridiani Planum. Subsequently, Spirit froze to death one winter.
Oh.
So Spirit lost mobility of one of its wheels. So we were driving backwards, dragging one of the front wheels like a boat anchor through the soil.
Oh, man.
And the rover drivers and scientists are very careful. we drove over an area that looked like it was going to be solid trafficable ground, but it turned out there was basically a hardpan layer on top of soil. Hardpan is kind of a indurated layer that's a little bit stiffer, so it didn't look like it was, loose sand, but it turns out we broke through and got mired in a deep sand pit, basically. And we were unable to extract the rover from the sand in spite of heroic efforts by the engineers, the rover drivers at JPL.
Yeah.
And the solar panel was tilted at a bad angle for the oncoming winter sun. So when the sun started getting lower and lower relative to the tilt of the solar panel, we simply were not getting enough power to keep the rover going. And although we tried to contact it again after that winter, we never heard from it again. So it basically just froze to death on Mars.
Oh, man. But as Opportunity, it's twin? Is it the...
Yep, Opportunity is its twin.
And that one's still going, right?
And that one's still going. We're now, what day is today? The
8th, yeah.
Yeah, we're now about 2 weeks away from the 14th anniversary of landing on Mars for Opportunity.
14 years,
yeah,
wow.
It's still going strong. And we are still actively exploring the geology of Meridiani Planum. We don't have all the instruments we had when we landed, but we're still making great scientific discoveries, even with the limited rover ability.
Well, how about that? So how is working with a rover on Mars different from looking at meteorites, maybe even Martian meteorites like the Allen Hills here on Earth? How is that different?
Well, here on Earth, I have the luxury of taking a sample into the lab and using state-of-the-art scientific equipment to tease out its story. On Mars, we have cameras that we can use to image the terrain. So right away, textures, and we have a microscopic camera. So textures allow us to make inferences about what the rock, how the rock might have been formed. We have a camera with 13 color filters on it, so we can do some limited spectroscopy of the rock. That helps us compare a limited set of mineralogical variations in the rocks. And then we have the alpha particle X-ray spectrometer, which allows us to do bulk compositions of surfaces. So between them, we can get a fairly good handle of the mostly the textures and bulk composition and to some extent mineralogy of a rock, and that helps us understand what processes might have formed the rock altogether. And to some extent, where Opportunity is a high-tech version of a 19th century terrestrial geologist. But obviously the spectrometer is better than what they had in the 19th century, and the chemical composition is as good as we could do then, and actually better for many elements. But we're still not at the cutting edge as you could do if you had a mobile laboratory up on Mars.
Yeah, definitely. And that's kind of your trade-off, right? Is like here, you can bring them to a lab with all the latest equipment and study these meteorites. But like you said before, like there's a certain amount of contamination that's going on with just the fact that a meteorite has come through the atmosphere and hit the surface of the Earth. You have to deal with that. But then you have limited instruments right there on Mars. So I guess you just kind of have these trade-offs.
Yep.
So another one that you mentioned, another infamous meteorite, was one called Orgueil, and that one's much earlier than the Allen Hills one, right?
Yeah. So Orgueil fell in France in 1864, if I remember right. Mm-hmm. And what's key here is it's a very primitive type of meteorite. It's a carbonaceous chondrite. The two-letter name for it is a Ci chondrite. These are amongst the most primitive meteorites that we have for study. Their bulk compositions basically are identical to what we see for the photosphere of the sun, excluding the most volatile elements like helium, hydrogen, and oxygen, and so forth. But if you could take the sun, a cubic kilometer of the sun, and condense out all the condensable matter, the composition would be very much like carbonaceous CI carbonaceous chondrite. So these have always been the touchstone for understanding the chemical evolution of the solar system. They are our basis for seeing who has varied from the original composition. But they're highly altered, so they're almost completely made up of clays and other low-temperature alteration phases. So the original high-temperature phases have been replaced. So at some point, these things were altered by water in their parent asteroid to the point where all that's left is basically clay. This makes them... This made Orgay susceptible to a nefarious individual attempting to prove something, what we don't know because we don't know who that individual was. But, I would call Orgay the Piltdown Man of meteorites. So Piltdown Man was this fake fossil made in about 1912, I think, to look like it had some of the attributes of an ape, but some of the attributes of a modern human, because someone thought that that's the way human evolution went. And they wanted to show that we had fossils that fit in with that theory. Well, Orgay, at some point, was broken open. And it turns out because this is clay, you can, if you get it good and wet, you can kind of break it open like clay. And then they had stuffed in terrestrial seeds and plant fragments and coal, and then put it back together and coated the outside with glue to make it look like it still had the fusion crust on it.
Oh my gosh.
And then this sample was sealed in a bell jar in a museum from 1864. So apparently it happened very early.
Yeah.
We don't know who did it. Or why, what were they trying to accomplish by this? Because it was going to be sealed in a bell jar.
Right.
Did they think someone was going to then take it out and look at it? I don't know. But this came to light in the 1960s then.
Oh.
So a well-known meteoriticist by the name of Ed Anders, very famous, very smart man, he led a study that was published 100 years later in 1964 in Science, where he uncovered, all of this forensic meteoritic work, where he showed that the seeds were terrestrial seeds, the coal fragments were in there, that glue had been used to put it back together and make it look like it was whole, and all of this. And so that's why this is an infamous meteorite for those who are in the know. Most people won't have heard of it, but
right.
Like I said, it's kind of the Piltdown Man of meteoritics.
Wow.
So someone had an agenda. For some reason they wanted to show that life could form on an asteroid or in space or something. I don't know, but obviously they had some agenda when they did this.
Yeah, I know, but seeds and glue are not really a good way to convince
No,
people.
no. Back in the mid 19th century, had it been opened up and studied then, maybe it would have caused quite a furor. But as far as I know, this was only discovered in a century later.
Wow. 100 years, people thinking this is some kind of capsule of extraterrestrial life. How about that?
Yeah, I know.
So, all of these kind of tell a story, and unfortunately, some of them, this particular one was a little bit of a lie. But, we are cracking these open to search for evidence of whatever we can find, right? Maybe the formation of a planet, maybe the formation of solar system, maybe the formation of life.
Yeah.
So, what... In a perfect world, I guess, what would you like to do? What would you like to study? What would you like to see and do to really maximize what you can find about learning more about our solar system and about life in the universe?
Well, I mean, that's kind of a difficult question for a scientist to answer because, truth be told, we're all paid to pursue our hobbies. And so we all have our own hobby horses. So as I mentioned, my particular interests are in igneous processes. On the Earth, Moon, Mars, asteroids. I like magmatic rocks, and I couldn't tell you why. It's just the way I am. So one of the things that's very curious about asteroidal igneous rocks is that asteroids were melted very early in the solar system, probably within a couple million years of the formation of the earliest known solids in the solar system. So something had to heat up relatively small objects, maybe a few hundred kilometers, 200 miles in diameter or in radius, something like that, to the point where they were melted and then cooled down, and then they completely shut off after that. So it was a very, very intense heat source that acted early, died out, and then never came back. We think we know what caused this, but there, the leading contender is radioactive heating by a very short-lived isotope of aluminum. It has a half-life of about 730 million years, and aluminum is a major element in rocks. So if you accumulate an asteroid early enough when there's this aluminum-27 still live, you've then encapsulated a very potent heat source inside that rock, and so that's what we think happened. But still, we can as scientists we can imagine this process going on, but geology is always much more complicated than our imaginations. So there are things that I don't understand, things that, as far as I know, no one really understands about how asteroids went from being primitive objects that accumulated from minerals formed in the solar nebula to basically a molten ball that then crystallized out igneous magmatic rocks similar to what we see on Earth. I would desperately like to be able to find out more about what was going on. What have we missed? Because we tend to think of things in the simplest terms. It was heated up, melted, crystallized. That's it. Well, we know that that's not all the story.
Yeah.
And I think all meteoriticists have in the back of their minds, for their particular hobby horses, just things they don't quite understand. They know the broader picture, but what are the finer details that went into this? We know we've got the basic story, but what are all the chapter and verse that go into this basic story? Wow. So that's what drives me, and it's all a matter of learning something new that pushes forth human knowledge. What I do is nowhere near applied science. It's pure basic science. So I can't talk to someone and say, tomorrow you're going to be able to have a better life because of what I do. Only if, unless you think a better life means knowing more. But you never know, because in general, a large fraction of basic research ultimately does find an application. Yeah. Right now, I don't know what that application might be, but I won't say there's never going to be some application for what I do. But for me, it's the sense of learning something that drives me.
Yeah. Why learn if you don't think it's going to end up, giving you a better life?
Yeah,
I mean, honestly, learning things kind of helps you understand things, helps things come together. To me, that makes me pretty happy. So I could see that, better understanding giving me a better life.
Yeah, well, I mean, humans have always been curious, and I suspect the reason we're curious is because it's beneficial for survival. Because, when you're out in the savannah hunting lions or hunting gazelles, if you see something moving the weeds over there, okay, is that a gazelle or is that a lion about to eat me instead? So, humans are geared toward being curious about their environment because it's a survival mechanism.
Yeah.
And for scientists, we have now transposed that, away from worrying about whether we're going to be eaten to just broad knowledge in general.
Well, I think last time we sat down with Dr. Burton, he said he kept talking about this time machine. How easy it would be, how nice it would be to just kind of hop in a time machine, watch these processes take place, and be like, that's how it takes place. I mean, then there's this whole philosophical idea of, well, is that going to alter the universe if you go back in time and watch these things? So, that was another tangent we could have gone on and we didn't, but but it would be nice to, for the, to improve our knowledge a little bit of how all this stuff works and comes together. All right, so Duck, I think that about wraps it up for today. So thank you so much for coming on the podcast
It's been a pleasure. I hope I've imparted something that makes sense to the listeners and that they will find interesting.
It's actually, we're talking about rocks if you think about it, but it's absolutely fascinating what you can find and the stories behind these rocks and what they tell you about the universe, and even just your trips to Antarctica are pretty fascinating as well. So again, thanks so much for coming on and telling the stories of these beautiful rocks and your trips to Antarctica. And hopefully we'll find some cool evidence of life, or you'll find that key ingredient as to why the asteroids did what they did.
yeah well, I hope so, and thank you very much for the invite.
Absolutely.
Houston, go ahead.
Stop of the space shuttle.
Roger, 0G, and I feel
The
fine.
shuttle has cleared the tower.
indeed for all mankind.
It's actually a huge honor to break a record like this.
Not because they are easy, but because they are hard.
Deborah Houston, welcome to space.
Hey, thanks for sticking around. So today we talked with Dr. Duck Middlefield about some of the cooler, infamous meteorites that have been discovered throughout the years, and then some interesting stories about Antarctica and how he's finding them. It's really a cool process, and he works with the ANSMET. It's the Antarctic Search for Meteorites. So if you want to learn more about ANSMET and some of the adventures that are going on in Antarctica and some of the curious findings in these meteorites, especially some that may or may not be life, it turns out that there were some, faked meteorites at the end of there, which is kind of disappointing, but that's okay. You can go to ares.jsc.nasa.gov to get the full scoop on all of these cool meteorites, and you can learn how to get your hands on one of these meteorite samples to study them. If you go to social media on the NASA Johnson Space Center accounts, or if you go to Ares or Astromaterials, NASA Astromaterials, we got pages on Facebook, Twitter, and Instagram where we like to share these stories. Just use the hashtag AskNASA on your favorite platform to submit an idea, or if you have a question about meteorites, or if you want to submit a new topic for the show, just make sure to mention it's for Houston. We have a podcast. So this podcast was recorded on January 8th, 2018. Thanks to Alex Perryman, Greg Wiseman, Tracy Calhoun, and Jenny Knotts. And thanks again to Dr. Duck Middlefield for coming on the show. We'll be back next week.